4 billion years ago, Mars had rivers, not small ones, not seasonal trickles, full permanent rivers, hundreds of kilometers long, cutting through valleys, feeding lakes, draining into what may have been an ocean covering the entire northern hemisphere of the planet. An ocean estimated to have held more water than the Arctic Ocean holds today. Mars had a thick atmosphere. It had a magnetic field. It had clouds. It had rain. By every measure we currently use to define habitability, early Mars was a candidate, and then, in geological terms, almost overnight, it lost everything. The atmosphere thinned to almost nothing. The magnetic field collapsed. The water froze, evaporated, or went underground. The rivers dried. The lakes disappeared. The ocean drained away into space, molecule by molecule, stripped by the solar wind over hundreds of millions of years. Today, the atmospheric pressure on the surface of Mars is less than 1% of Earth's. The average surface temperature is minus 60 degrees Celsius. Liquid water cannot exist on the surface. The sky is a thin butterscotch haze. The landscape is dry, frozen, irradiated, and silent. Mars did not slowly wind down. It was killed. And the weapon that killed it was something Earth has, and Mars lost. Something so fundamental that without it, no planet in the inner solar system can survive. That is what we're going to find out today. Thank you for spending your time here among the stars. If you'd like to support the channel, subscribing will mean a lot. Now let's begin. Mars and Earth are siblings. They formed at roughly the same time, approximately 4.5 billion years ago, from the same rotating disk of gas and dust that surrounded the young Sun. They are neighbours in the inner solar system, separated by an average distance of about 225 million kilometres. They are both rocky terrestrial planets with solid surfaces, internal structures of iron cores and silicate mantles, and, critically, both sit within or near the Sun's habitable zone, the region where liquid water can theoretically exist on a planetary surface. By the standards of planetary science, they should have had similar fates. They did not. Earth today is a world of liquid oceans, a thick nitrogen-oxygen atmosphere, a global magnetic field, active plate tectonics, and 4 billion years of continuous biological evolution. It is, as far as we know, the only world in the universe confirmed to harbour life. Mars today is a frozen desert. Its atmosphere is 95% carbon dioxide and so thin that the total atmospheric pressure at the surface is equivalent to what you would experience at an altitude of 35 kilometers above Earth, well above the stratosphere, in the realm where spacecraft operate. No liquid water exists on the surface. No confirmed biology of any kind has ever been detected there. The divergence between these two planets is one of the most important questions in planetary science, not just because it tells us about Mars, but because it tells us about Earth, about why we are here, about how contingent our existence is on a specific set of conditions that could easily have been otherwise. Because here is the truth that planetary science has arrived at, after decades of spacecraft missions, rover deployments, atmospheric studies, and geological analyses. Earth did not survive because it was better positioned. It did not survive because it was larger, or because it formed from superior material, or because the Sun was kinder to it. Earth survived because of a series of factors, some physical, some geological, some the product of a single catastrophic event early in the solar system's history, that Mars happened not to share. Earth got lucky. And understanding exactly how lucky requires us to understand exactly what Mars lost, when it lost it, and why. The image of Mars that most people carry, the rust-red desert, the thin atmosphere, the barren silence, is not the planet's whole story. It is the planet's current state, and current states, in planetary science, are not permanent conditions. They are snapshots in a 4 billion year film. The early Mars film looks very different from the final frame, the ancient atmosphere. Mars today has an atmospheric pressure of roughly 600 pascals at the surface, about 0.6% of Earth's sea level pressure of 101,325 pascals. This atmosphere is almost entirely carbon dioxide, with trace amounts of nitrogen, argon, and other gases. It is far too thin to support liquid water on the surface. At this pressure, water exposed to the Martian surface would immediately either freeze or boil away, depending on temperature. But geological and mineralogical evidence tells us that early Mars had a much thicker atmosphere. The presence of ancient river valleys, lake beds, delta formations, and carbonate minerals, all of which require liquid water to form, proves that liquid water existed on the surface of Mars for extended periods in its early history. To have liquid water on the surface, Mars must have had an atmospheric pressure high enough and temperatures warm enough to keep water in liquid form. Models suggest the early Martian atmosphere may have had pressures ranging from a fraction of a bar up to several bars, comparable to or even exceeding Earth's current atmospheric pressure. Where did it go? We will get to that. The ancient water. The evidence for ancient Martian water is overwhelming and comes from multiple independent lines of inquiry. Valley networks, systems of branching channels clearly carved by flowing water, are visible across the ancient southern highlands of Mars, particularly in terrain dated to the Noachian period, roughly 4.1 to 3.7 billion years ago. These networks resemble river drainage systems on Earth, with tributaries joining main channels, meanders preserved in the rock, and clear evidence of sustained water flow rather than single catastrophic flood events. The Curiosity rover, operating in Gale Crater since 2012, has found abundant evidence that the crater once contained a lake, possibly for millions of years. The sedimentary layers it has driven through are characteristic of material deposited in standing water. The chemical composition of the rocks includes minerals that form only in the presence of liquid water, including phyllosilicates, clay minerals, that require sustained water contact to form. The Perseverance rover, currently operating in Jezero Crater, landed in what is geologically identified as an ancient river delta, a fan-shaped deposit of sediment laid down where a river once flowed into a lake. The delta structure is preserved in extraordinary detail, visible from orbit and confirmed at ground level by Perseverance's instruments. The Omega instrument on ESA's Mars Express spacecraft has mapped the global distribution of hydrated minerals, minerals that incorporated water into their crystal structure as they formed, across the Martian surface. These minerals are concentrated in the ancient southern highlands, consistent with a period of widespread surface water in Mars's early history. Perhaps most dramatically, Mars Reconnaissance Orbiter data has revealed what appears to be the ancient shoreline of a northern ocean, a subtle but consistent topographic feature running for thousands of kilometers around the northern lowlands at an elevation consistent with a large body of standing water. Early Mars, in the Noachian and early Hesperian periods, was not the desert we see today. It was a planet with an active water cycle. Rain fell, rivers ran, lakes accumulated. An ocean may have covered a third of the planet's surface, the ancient magnetic field. One more element of early Mars that we know existed and no longer does, a global magnetic field. We know Mars once had a magnetic field because of the magnetization patterns preserved in its ancient crust. When rocks form from cooling magma, magnetic minerals within them align with the ambient magnetic field, like compass needles frozen in place as the rock solidifies. Variations in the direction and intensity of this crustal magnetization, measured from orbit by the Mars Global Surveyor spacecraft, reveal a pattern consistent with a past global magnetic field, including, intriguingly, alternating bands of normal and reversed polarity, similar to the magnetic striping patterns found on Earth's ocean floor that record the history of our own magnetic field reversals. Mars had a magnetic field, ancient, active, and, for a time, protective. It is gone now, and its loss was the beginning of the end for everything else. To understand why the loss of Mars's magnetic field was catastrophic, we need to understand what a planetary magnetic field actually does. Earth's magnetic field, the magnetosphere, is generated by the movement of electrically conducting liquid iron in the outer core. As the planet rotates and heat flows outward from the inner core, the liquid iron outer core undergoes convection. Enormous, slow currents of molten metal circulating under the influence of the planet's rotation. These moving electrical conductors generate a magnetic field through the same principle that underlies every electric generator ever built. Moving charges create magnetic fields. The result is a global magnetic field roughly similar in structure to that of a bar magnet, with field lines emerging from near the south geographic pole, arching through space around the planet and re-entering near the north geographic pole. This field extends far into space, the magnetosphere, creating a vast protective bubble around the planet. What does this bubble protect against? The solar wind. The sun continuously emits a stream of charged particles, mostly protons and electrons, in all directions. This solar wind moves at speeds of 400 to 800 kilometers per second and carries with it a magnetic field, the interplanetary magnetic field. When the solar wind encounters a planet with a global magnetic field, the planetary field deflects the solar wind particles, preventing them from directly striking the upper atmosphere. Without this deflection, the solar wind particles would directly interact with the upper atmosphere, transferring energy to atmospheric molecules and, critically, providing enough energy to accelerate those molecules to escape velocity. The solar wind, given direct access to an unshielded atmosphere, strips it away. Molecule by molecule, over millions and billions of years, the atmosphere erodes into space. This process, atmospheric sputtering and escape driven by solar wind interaction, is exactly what happened to Mars after it lost its magnetic field. Mars's magnetosphere collapsed somewhere between 4.2 and 3.7 billion years ago. The evidence from crustal magnetization suggests it happened relatively abruptly in geological terms, possibly within a few hundred million years. The exact cause is debated, but the most widely accepted explanation involves the cooling of Mars's small iron core. Mars is smaller than Earth, roughly half the diameter and about 1/10 the mass. Smaller planets cool faster. As Mars's core cooled, the temperature difference between the inner and outer core decreased. Convection in the liquid outer core weakened, and without vigorous convection, the dynamo that generated the magnetic field could not be sustained. The field weakened, became patchy, and eventually collapsed. Once the magnetic field was gone, the solar wind had direct access to the Martian atmosphere, and the Sun 4 billion years ago was significantly more active than it is today, emitting stronger solar winds and more frequent and intense solar energetic particle events. The atmospheric stripping accelerated. NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, has been orbiting Mars since 2014, specifically designed to study the interaction between the solar wind and the Martian atmosphere. MAVEN has directly measured the current rate of atmospheric escape from Mars and confirmed that the solar wind is today stripping approximately 100 grams of atmosphere per second from the planet. That number sounds small, but multiplied across billions of years, and accounting for the fact that the ancient solar wind was much more intense, it represents an enormous loss of atmospheric mass. The thick early atmosphere that allowed liquid water to exist on Mars's surface was gradually, relentlessly, stripped into space by a solar wind that met no magnetic resistance. The atmosphere thinned, temperatures dropped, water could no longer remain liquid on the surface. It froze into the permafrost and polar ice caps, or escaped into space as water vapor was broken apart by solar ultraviolet radiation, a process called photodissociation, with the lighter hydrogen escaping to space and the heavier oxygen remaining behind, contributing to the rust-red iron oxides that give Mars its distinctive colour. Mars's death was not an explosion. It was a slow bleeding out, a planet that lost its shield and then lost everything the shield was protecting. If Mars lost its magnetic field because its core cooled too quickly, the obvious question is, why didn't Earth's core cool the same way? The answer involves several factors that, taken together, explain one of the most consequential differences between the two planets. Factor 1. Size. Earth is significantly larger than Mars. With roughly 10 times the mass, Earth has a much larger thermal reservoir. more heat stored in its interior from the energy of formation and from the decay of radioactive elements. A larger planet simply takes longer to cool. Earth's core is still hot enough, over 5,000 degrees Celsius at the inner core boundary, to maintain the temperature difference between the inner and outer core that drives convection and sustains the dynamo. Mars, with its smaller mass, cooled faster. The thermal engine that powered its magnetic field ran out of fuel sooner. Factor 2. Radioactive heating. A significant fraction of Earth's internal heat comes not from the primordial heat of formation, but from the ongoing decay of radioactive isotopes, primarily uranium-238, thorium-232, and potassium-40, distributed through the mantle and core. These isotopes decay slowly, releasing heat over billions of years, supplementing the primordial heat and slowing the overall cooling of the planet. The amount of radioactive heating a planet experiences depends on its composition, specifically the concentration of these radioactive elements in its interior. Earth's composition appears to have provided enough radioactive heating to sustain its internal heat engine over the age of the solar system. Mars's smaller size and possibly different composition gave it less of this supplementary heat source. Factor 3. The Moon and tidal heating. This is perhaps the most dramatic factor, and the one most directly tied to luck rather than any inherent property of the Earth itself. Approximately 4.5 billion years ago, very early in the solar system's history, Earth experienced a catastrophic collision. A Mars-sized protoplanet, which planetary scientists call Theia, struck the proto-Earth at an oblique angle. The collision was not a head-on impact. It was a glancing blow, but at a scale almost impossible to comprehend. The energy released was enormous. Both bodies were partially melted and disrupted. Material from both the impactor and the proto-Earth was flung into orbit around Earth, and this material eventually coalesced to form the Moon. This event, the giant impact hypothesis, is the currently accepted explanation for the Moon's formation, and is supported by a broad array of evidence, including the similarity in isotopic composition between Earth and Moon rocks, the Moon's relatively low iron content consistent with forming primarily from the mantles of both bodies rather than their cores, and the angular momentum of the Earth-Moon system. But the giant impact did more than create the Moon. It also had profound consequences for Earth's internal structure and heat budget. The impact partially remelted Earth's interior, redistributing heat and mixing material. It may have contributed to the differentiation of Earth's core, the separation of iron and nickel into the core, leaving a silicate mantle above, and the Moon, once formed, began exerting tidal forces on Earth that continue to this day. Tidal heating from the Moon, the flexing of Earth's interior by the Moon's gravitational pull, provides a small but non-negligible contribution to Earth's internal heat budget. More importantly, the Moon's tidal influence affects the dynamics of Earth's core, potentially influencing the convection patterns that sustain the geodynamo. Mars had no such event. No giant impact created a large moon for Mars. Mars has two tiny moons, Phobos and Deimos, which are almost certainly captured asteroids with negligible tidal influence. Mars had no tidal heating from a large companion. The Moon, in this framing, is part of why Earth still has a magnetic field. The catastrophic collision that created it was, from the perspective of long-term planetary habitability, one of the most fortunate events in Earth's history. Factor 4. Plate tectonics. Earth has plate tectonics. Mars does not. Plate tectonics, the movement of large sections of Earth's lithosphere relative to each other, driven by convection in the mantle below, is a critical part of Earth's long-term habitability in multiple ways. For the magnetic field specifically, the connection is indirect but real. Plate tectonics is a mechanism for releasing heat from Earth's interior, maintaining the temperature gradients that drive mantle convection, which in turn influences core convection and the geodynamo. Mars shows no evidence of global plate tectonics. It has a one-plate lithosphere, a single rigid shell rather than the mosaic of moving plates that characterizes Earth. This means heat can only escape from Mars's interior through conduction and through localized volcanic activity, rather than through the efficient heat-releasing mechanism of plate subduction. Paradoxically, the absence of plate tectonics may have contributed to Mars's core cooling faster in some respects, and to the planet retaining heat in others in ways that did not sustain the dynamo. The details are still debated, but the connection between plate tectonics, heat flow, and magnetic field sustainability is an active area of research. We've established that Mars lost its magnetic field and that this allowed the solar wind to strip its atmosphere. But the loss of water from Mars is a more complex story than simple atmospheric stripping, and it is worth tracing in detail. Mars's water disappeared through 3 distinct pathways. Pathway 1: escape to space. With the magnetic field gone and the atmosphere thinning, water vapour in the upper atmosphere was exposed directly to solar ultraviolet radiation. UV photons carry enough energy to break apart water molecules, a process called photodissociation. A water molecule hit by a UV photon splits into its constituent atoms, 2 hydrogen atoms and 1 oxygen atom. Hydrogen is the lightest element. Even at the relatively low temperatures of the upper atmosphere, a significant fraction of hydrogen atoms move fast enough to exceed Mars's escape velocity, the speed required to leave the planet's gravitational field entirely. Mars's escape velocity is only 5 km per second, compared to Earth's 11.2 km per second. The lower gravity makes it significantly easier for light gases to escape. The hydrogen atoms produced by photodissociation of water vapour escape to space. The oxygen atoms, being heavier, mostly remain, contributing to the oxidation of iron in the surface rocks, turning them the rust-red colour that gives the planet its name. Mars is literally rusting. The red colour of Mars is the remnant of the water that used to be there. MAVEN has measured the current rate of hydrogen escape from Mars's atmosphere and confirmed that it is occurring at a rate consistent with the loss of significant water over geological time. Pathway 2: freezing into permafrost and polar ice. Not all of Mars's water escaped to space. A significant fraction froze. As Mars's atmosphere thinned and temperatures dropped below the freezing point of water permanently across most of the planet, liquid water on the surface transitioned to ice. This ice, buried under dust and rock over billions of years, forms a global permafrost layer, a layer of ice-cemented soil extending to significant depth across much of the planet. The polar ice caps of Mars contain both water ice and carbon dioxide ice. The North Polar Cap is predominantly water ice covered by a thin seasonal layer of carbon dioxide frost. The South Polar Cap contains a permanent layer of carbon dioxide ice, overlying a base of water ice. Radar measurements by the MARSIS instrument on Mars Express and the SHARAD instrument on Mars Reconnaissance Orbiter have mapped subsurface ice deposits across the planet. The volume of water stored as ice in Mars's subsurface and polar caps is enormous. Estimates suggest that if all of Mars's known water ice were melted and distributed evenly across the surface, it would form a global ocean roughly 35 meters deep. Mars did not lose all its water to space. Much of it is still there, locked in ice, waiting. Pathway 3: chemical incorporation into minerals. Water interacts chemically with rock. When liquid water contacts certain minerals, it can be incorporated into the mineral crystal structure, forming hydrated minerals, clay minerals, sulfates, carbonates, that lock water molecules into solid rock. The extensive deposits of hydrated minerals mapped across Mars's ancient terrain represent a significant reservoir of chemically bound water, water that reacted with the ancient Martian crust and became part of the rock itself. This water is not recoverable by simply warming the planet. It is chemically bound, requiring temperatures high enough to drive dehydration reactions to release it. The total amount of water incorporated into Martian minerals is uncertain, but it is likely substantial, representing a significant fraction of the total water budget of early Mars. There is one more chapter in Mars's death that deserves its own section, and it involves the largest volcano in the solar system. Olympus Mons is a shield volcano on Mars with a height of approximately 21.9 kilometers above the Martian datum, the equivalent of sea level on Mars. It is nearly 3 times the height of Mount Everest above Earth's sea level. Its base is approximately 600 kilometers in diameter. large enough to cover the entire state of Arizona. Its summit caldera is 80 kilometers wide and 3 kilometers deep. It is, by any measure, a staggering geological structure, and its very existence tells us something important about why Mars died the way it did. On Earth, volcanoes form chains, the Hawaiian island chain being the classic example. The Pacific tectonic plate moves over a stationary hotspot in the mantle, and as it does, a chain of volcanic islands is built, each one older than the last in the direction of plate movement. No single volcano on Earth grows to extraordinary size because the plate keeps moving, constantly shifting the volcanic activity to new locations. On Mars, there is no plate movement. The lithosphere is stationary over the mantle hotspot. All of the volcanic activity in the Tharsis region, the massive volcanic plateau on which Olympus Mons sits, has been focused on the same spot for billions of years. The same location has been erupting, building up material for an almost incomprehensible length of time. The result is Olympus Mons, a volcano that kept growing and growing because there was nothing to move it away from its heat source. But Olympus Mons is more than a geological curiosity. It is a symptom of Mars's fundamental geological problem, and one of the reasons Mars died. Active volcanism on Earth is intimately connected to plate tectonics. The subduction of oceanic plates into the mantle drives volcanic activity at subduction zones. Mid-ocean ridge volcanism creates new oceanic crust. This volcanic activity is distributed globally, releases heat efficiently from the interior, and, critically, plays a role in the long-term carbon cycle. Volcanoes release carbon dioxide. Weathering of rocks by liquid water absorbs carbon dioxide, locking it into carbonate minerals. Subduction carries these carbonate minerals back into the mantle, where they are heated, and the carbon dioxide is eventually released again through volcanism. This carbon silicate cycle, the long-term geological carbon cycle, regulates Earth's atmospheric carbon dioxide levels over geological timescales, acting as a thermostat for the planet's climate. Mars had no global carbon silicate cycle. Without plate tectonics, there was no efficient mechanism for returning subducted carbonates to the atmosphere. The volcanism that did occur was concentrated in the Tharsis region, not distributed globally. The geological thermostat that Earth has never developed on Mars. Furthermore, the massive Tharsis volcanic complex may have actually contributed to Mars's decline. The enormous mass of volcanic material deposited in the Tharsis region created a gravitational anomaly that caused a true polar wander event, a reorientation of the entire planet relative to its rotation axis. This reorientation, which occurred roughly 3.5 billion years ago, destabilized the distribution of water ice and may have contributed to the disruption of the early Martian climate. The very volcanism that once helped warm Mars and provide atmospheric gases eventually contributed to the planet's geological dysfunction. The absence of plate tectonics meant Mars could not regulate itself. It could not recycle. It could not maintain the global geological processes that Earth uses to sustain its habitability over billions of years. By now, the picture of Mars's death is fairly complete, but it is worth standing back and listing clearly and explicitly everything Earth has that Mars lost or never had, because the list is both longer and more interconnected than it might initially appear. A sustained magnetic field. Earth's geodynamo has been running for at least 3.5 billion years, possibly longer. It deflects the solar wind, protects the atmosphere, and shields the surface from harmful charged particle radiation. Mars's dynamo shut down around 4 billion years ago and never restarted. A thick, stable atmosphere. Earth's atmosphere is 78% nitrogen and 21% oxygen, at a surface pressure of 101,325 pascals, sufficient for liquid water, for the greenhouse warming that keeps average surface temperatures above freezing, and for the chemistry of life. Mars's atmosphere is 95% carbon dioxide at a surface pressure of roughly 600 pascals, insufficient for any of these functions. Plate tectonics. Earth's moving plates recycle the crust, regulate the carbon cycle, distribute heat from the interior, drive mountain building, create diverse habitats, and maintain the long-term geological stability that has allowed complex life to persist for hundreds of millions of years. Mars has none of this. Liquid water on the surface. Earth has had liquid surface water continuously for at least 3.8 billion years, possibly longer. Mars has had none for at least 3 billion years, possibly longer. A large moon. Earth's moon stabilizes our planet's axial tilt, the angle at which Earth's rotation axis is tilted relative to its orbital plane, within a relatively narrow range of about 22.1 to 24.5 degrees over long timescales. This stability is important for climate stability, because the axial tilt controls the severity of seasons. Mars, with only tiny moons, has no such stabilization. Mars's axial tilt has varied chaotically between near zero and over 60 degrees over geological time, causing dramatic climate shifts that would have been deeply destabilizing for any emerging biology, a size large enough to retain internal heat. Earth's mass, 10 times that of Mars, has allowed it to retain enough internal heat over 4.5 billion years to sustain its geological engine. Mars cooled too fast. The right amount of radioactive heating. Earth's interior contains enough radioactive isotopes, uranium, thorium, potassium, to supplement its primordial heat and slow its cooling over the age of the solar system. Mars, smaller and possibly compositionally different, had less of this supplementary heat source. Each of these factors reinforces the others. The magnetic field protects the atmosphere. The atmosphere allows liquid water. Liquid water enables the carbon cycle. The carbon cycle, mediated by plate tectonics, regulates the climate. Climate stability allows biology. Biology on Earth has actually contributed to maintaining the atmosphere. The oxygen in our atmosphere is entirely biological in origin, produced by photosynthetic life over the past 2.4 billion years. It is a web of interconnected systems, each one supporting the others. Remove one thread, as Mars removed the magnetic field, and the web begins to unravel. The atmosphere thins, the water disappears, the temperature drops, the geology stagnates, and the planet dies. This question sits at the intersection of planetary science and human ambition, and it deserves a serious answer. Could Mars be restored? Could the processes that killed it be reversed? The honest answer, based on current science, is partially, with enormous difficulty over very long timescales, and with fundamental limitations that may be impossible to overcome. The atmosphere problem. Thickening Mars's atmosphere is theoretically possible. Several proposals have been advanced, ranging from releasing the carbon dioxide currently frozen in the polar ice caps and the subsurface permafrost by warming the planet, to importing volatile rich material from the outer solar system. Calculations suggest that releasing all of Mars's known CO2 reserves would increase atmospheric pressure to perhaps 1.2% of Earth's, still far too thin for liquid water or human survival without life support. A 2018 study by Bruce Jakosky and Christopher Edwards, published in Nature Astronomy, concluded that the accessible CO2 on Mars is insufficient to terraform the planet to Earth-like conditions using any currently known technology. The atmosphere that was lost to space over billions of years cannot simply be recovered from what remains. The magnetic field problem. This is the most fundamental obstacle. Without a global magnetic field, any atmosphere we built for Mars would be continuously stripped by the solar wind. On timescales of millions of years, the restored atmosphere would bleed away into space, just as the original one did. Proposals for artificially generating a Martian magnetic field exist, including a proposal, discussed seriously by NASA scientists, to place a magnetic dipole shield at the Mars L1 Lagrange point, the gravitational balance point between Mars and the Sun, to deflect the solar wind before it reaches Mars. The proposal is technically speculative but not physically impossible. Whether such a shield could be built and maintained is far beyond current engineering capability. Restarting Mars's internal dynamo, the approach that would be most permanent, appears essentially impossible with any technology we can currently imagine. The core has cooled. The convection has stopped. Reheating a planetary core from the outside is not a solvable engineering problem in any near-term sense. The time problem. Even if we could solve the atmospheric and magnetic field problems, terraforming Mars to Earth-like conditions would take thousands to millions of years at minimum, even under optimistic assumptions. The geological processes that built Earth's habitability operated over billions of years. There is no shortcut. For near-term human presence on Mars, which multiple space agencies and private companies are actively planning, the approach is not terraforming but rather working within Mars's current conditions. Pressurized habitats, life support systems, in situ resource utilization, extracting water from the permafrost, oxygen from the CO2 atmosphere. These are engineering challenges, not planetary scale transformation. Mars cannot be brought back to what it was. What it was is gone. The atmosphere is in space. The water is mostly locked in ice or chemically bound in rock. The magnetic field is not coming back without technological intervention that doesn't yet exist. The lesson of Mars is not a roadmap for recovery. It is a warning about how fragile the conditions for habitability are, and how quickly they can be lost once the underlying planetary machinery begins to fail. There is a temptation when discussing the death of Mars to treat it as a purely academic matter. An interesting geological story about a neighbour planet, remote from our own lives and concerns. But the story of Mars is, in a very real sense, a story about Earth. About what Earth is, about why it is the way it is, and about how unlikely it is that it turned out this way at all. Consider the chain of contingency that produced habitable Earth. Earth formed at the right distance from the Sun, close enough to be warm, far enough to avoid the fate of Venus, which sits just inside the inner edge of the habitable zone, and has experienced a runaway greenhouse effect that has raised its surface temperature to 465 degrees Celsius. Mars sits just outside the outer edge, or close enough that, once its atmosphere thinned, it fell below the threshold for liquid water. Earth formed with the right mass, large enough to retain its internal heat over billions of years, large enough to hold a thick atmosphere against the pull of both gravity and the solar wind, large enough to sustain plate tectonics. Earth was struck by Theia, a random collision with a Mars-sized protoplanet, which created the Moon, stabilized our axial tilt, possibly contributed to the differentiation of our core, and provided tidal heating that may have influenced our dynamo. This collision was not inevitable. It was a specific event in a chaotic early solar system. In many possible solar system histories, it does not occur. Earth retained plate tectonics, a process that may be rare among rocky planets, which has regulated our climate, recycled our crust, driven our geological carbon cycle, and maintained the conditions for life over billions of years. Earth evolved photosynthetic life, which transformed our atmosphere, producing the oxygen that now makes up 21% of the air we breathe, and creating the ozone layer that protects the surface from ultraviolet radiation. Without the oxygen atmosphere produced by biology, Earth's surface would be far more hostile than it is today. Each of these factors is contingent. Each could have been otherwise. In a solar system where Earth formed slightly closer to the Sun, or slightly smaller, or where the Theia impact never occurred, or where plate tectonics never developed, or where life never evolved photosynthesis, in any of those possible histories, Earth might look more like Mars than it does today. We look at Mars and we see what happens when the chain breaks. When one link, the magnetic field, the size, the geological activity, is missing or fails, the whole system unravels, the planet dies, and we look at Earth, and we should feel something beyond the casual familiarity that comes from living here all our lives. We should feel the contingency of it, the fragility of it, the specific, unlikely, non-guaranteed nature of what we have. Mars had rivers once. It had lakes, and possibly an ocean. It had a thick sky and a warm enough climate that rain fell and collected and flowed downhill and stood in basins for millions of years. And then it lost its magnetic field, and the solar wind found its atmosphere, and the air thinned, and the water froze or escaped or turned to rust in the rocks, and the rivers dried, and the lakes disappeared, and the sky became a thin butterscotch nothing that offers no protection and holds no warmth. And it has been that way for 3 billion years. Earth has been alive for 4 billion, continuously, without interruption. through 5 mass extinctions, through ice ages, through asteroid impacts, through volcanic super eruptions. Through all of it, the magnetic field held, the atmosphere persisted, the water stayed liquid, the geology kept cycling. Not because Earth is special in any cosmic sense, not because the universe arranged things for our benefit, but because a specific set of conditions, some the product of Earth's size and composition, some the product of a random catastrophic collision early in the solar system's history, some the product of biological evolution, happen to align and happen to persist. Mars shows us what happens when they don't. We are here because Earth got lucky, and Mars shows us in detail exactly what kind of luck that was. Take a breath. That air, that thin, oxygen-rich, nitrogen-dominated, magnetically protected, geologically recycled, biologically produced air is not guaranteed. It is not permanent. It is the product of 4 billion years of contingency that could have broken any number of ways. It didn't. That is worth knowing and worth protecting. Subscribe, because now you know